Hello and welcome again. As announced in the previous video, we will make the switch to natural coordinates in this video. The reason for doing so is that the geometry of an element is not always a nice rectangular as we used in the previous video. To make the drawings easy to understand, we will still be using a rectangular element in this video, but the methodology can be extended to irregular shapes as well, as you will see in the next video actually. I know we have discussed the natural coordinates before, but just to refresh your mind, I will quickly go over it again. The basic idea is that we normalize everything. In other words, we want to have the same unit length in both directions. For rectangular parts, that means that rather than the Cartesian element of length L and width W as you see on the left, we get an element with the coordinates ranging from -1 to 1. Furthermore, in the natural coordinate system, you will always have a rectangular element, even if the element in the Cartesian coordinate system has an irregular shape. The most important is that we have a way to transform the element from one coordinate system to another. We will derive it here for this straightforward case, but this translation is different if the element has a different geometry. The general approach, however, will stay exactly the same. Now, to start with, if we look at the location of the origin, we can immediately see that the origin is no longer in the corner of the element, but rather in the middle. Hence we will have to subtract 1 from the coordinate system for both eta and xi. Focusing on xi, we can see that the length L becomes a length of 2. Hence we need to multiply the x-coordinate with 2 divided by L to get the same length. Then we also have to subtract 1 to move the origin, and that is the transformation going from x to xi. In a similar way, we see that the width W becomes a length of 2 as well. Hence, to obtain eta, we need to multiply y by 2 over W, and again subtract 1 since we have moved the origin. We can also define the other transformation, obtaining x and y as a function of eta and xi. In that case, we have to shift by half the length and half the width to move the origin, and multiply by half L and half W. Of course, if you don't trust me, you can always check these transformations for yourself. Now, in this case, xi is only dependent on x, and eta is only dependent on y. But this is not always the case. If you have an irregular shape, both xi and eta will depend on both x and y. This will not make the methodology different, but you have to take that into account in your calculations, of course. Just to remind you of the transformation functions between the coordinates and the shape functions we have derived in the Cartesian coordinates in the previous video, I'm repeating them here. To derive the shape functions in the natural coordinate system, we could do the complete derivation again. But we can also fill in the expression for x and y into the shape function we have obtained before. This sounds like the easy way, so let's take that route. If we do this for ni, we obtain a quarter times 1 minus xi times 1 minus eta. For nj, we get 1 quarter times 1 plus xi times 1 minus eta. For nm, we get 1 quarter times 1 plus xi times 1 plus eta. For nn, we get 1 quarter times 1 minus xi times 1 plus eta. As you can already see, it is a bit easier to find the system in these shape functions. You always have a combination of 1 plus or minus xi and eta, and then you have all permutations of it. This is one of the advantages of using natural coordinates actually. Now this already concludes the video about the natural coordinates and the shape functions in terms of the natural coordinates. While it may seem a trivial step because of the rectangular element being transformed into, well, a rectangular element with equal sides of length 2, it is in reality a very powerful transformation that is generally applicable. In one of the coming videos, we will start from these shape functions to derive the stiffness matrix for a general quadrilateral element. And there, the functions to translate between the Cartesian and natural coordinate system will be used again as well. But first we make a small sidestep to the isoperimetric elements in the next video. See you there.